Hello student, hi, good evening. So today we are going to discuss about voltage buffer. Okay, so which is the application of the common collector amplifier, or we can say common ammeter, common collector amplifier, or we can say ammeter follower. Okay, so the most important application of common collector amplifier or ammeter follower is the voltage buffer. What is the most important application? That is what. See, what if I tell you, like, I have one signal. This is Vi of t in millivolt. This is 200, whose peak is varying from -200 to +200, which is the function of time. And this signal I am going to apply, and this signal has input, input resistance of 100 kilo ohm. And here, this is what the signal. Okay, so let's see, this is my signal, input signal. So this is my input signal, Vi. If I will, so this is my signal whose input resistance is 100 kilo ohm. So what if I tell you that if I will apply, if I tell you like that, I'm going to apply this signal to the loudspeaker. So here is my loudspeaker. Let's say this is my loudspeaker. If I will connect directly this input signal, let's say it is a voice signal, that I'm going to connect this to a loudspeaker, and whose load resistance is of 1 kilo ohm resistance. Okay, so this is what loudspeaker. Now here, am I audible properly? This input signal here means what we are getting at the loudspeaker, what strength of this signal we are getting at the output, okay, across the load. How much? See, we are going to we are just directly connecting this signal to the load without any amplifying device. Then what happens? So then there is a large amount of reduction in the signal. Large amount of reduction in the signal means there is a attenuation in the signal. How much attenuation is there? We will see it. Let's say this is my output voltage. This output voltage is equal to how much? By applying voltage division rule, which is nothing but 1K into 200 divided by 100 plus 1K. 100 plus 1K, this is in millivolt. How much I will get here? I will get here equal to how much? Equal to 1.99 millivolt. 1.99 millivolt of signal that I will get here across the load resistance of this loudspeaker, if I will connect my input voice signal directly to the load. Yes, without any amplifying device. So you see, 1.99 means it is approximately 2 millivolt. Approximately I am getting here 2 millivolt. Okay, out of 200 millivolt. So where 198 millivolt has attenuated. Okay, so means if you see here how much attenuation is there, 99% of attenuations that we are getting if we connect the input voice signal directly to the load. Yes, without any amplifying device. Yes, so that is what we see the important role of common collector amplifier, which is ammeter follower. So let's see here. So you see how much reduction is there. This is 2 millivolt means we are getting negligible amount of strength of this signal at the load, and we are not hearing any sound of input signal. Okay, so because if we are applying directly to the load this input signal, now what we are going to do, I'm just going to do what I'm going to connect here one amplifier. Yes, one amplifier. So this amplifier is my common collector amplifier, which is nothing but the ammeter follower. Let's see this common collector amplifier, which part of common collector amplifier play the important role in case of voltage as a voltage buffer. Let's see. So, and with this, by using this common collector amplifier or ammeter follower, we get the significant amount of improvement at the output. Okay, at the output side across the load. So let's see here. This is my common collector amplifier, common collector amplifier, or we can say ammeter follower. This is what ammeter follower. Now see here, this is my collector terminal, which is grounded. Okay, and this is my NPN transistor, and here is my base. Through the base I am connecting what? Input voice signal. So this is my Vi of t here. Okay, so here is my load. load resistance. Load resistance, this is what? RL, and this is my output. Okay, so if we see what is the important part, so that we can get from this common collector amplifier, this is my RSig. Okay, so whose resistance is 100 kilo ohm. Okay, so now see important parameter in case of common collector amplifier. First is what here? Input resistance. Okay, this is input resistance. How much input resistance is there? If you see here, Rin is equal to, let's say current gain is beta, which is current gain of common emitter amplifier. Rin is equal to what? Rin is equal to beta plus 1 into Re is this resistance. Okay, so from here, this is my Re resistance, Re plus RL. See, this is what input resistance of what? Common collector amplifier or emitter follower. What is output resistance here? If you see the output resistance which we are seeing from our load side, so this is my output resistance here. Output resistance, how much we can see the output resistance from the load side, that is equal to R0 is equal to what? R0 is equal to Re. Similarly Re, this is reflections of resistance. If you see, Re is equal to Rsig, R is equal to Rsig divided by beta plus 1. What? Beta plus 1. So this much amount of resistance that we are getting at the output. So this is what? Beta. This is what? Beta plus 1. So you see, input resistance is very high, output resistance is very low. Okay, so very low. So means if you see input resistance that we are getting approximately in the order of 100 kilo ohm. Yes, and output resistance here we are getting in the order of 10 ohm. So this is what the important application here. And the voltage gain that we get here in case of common collector amplifier or emitter follower, that is approximately equal to what? 1. Okay, so this is the common collector amplifier or emitter follower. Now we are going to see the application of this common collector amplifier or emitter follower for the input signal that we apply to this. Okay, so how it buffer the input signal, how the common collector amplifier buffer the input signal with significant improvement at the output side across the load of the loudspeaker. So let's see here, we are going to see. This is what, if you see here, this is my input signal. Input signal was what? This. Okay, so this is my input signal V in millivolt. So here whose peak is 200 to minus 200 millivolt. Okay, so now and here this signal Vi. Okay, I'm just now connecting this signal Vi whose input resistance Rsig, whose input resistance is what? 100 kilo ohm, and now I'm just connecting this to a common collector amplifier. This is my common collector amplifier. Okay, common collector amplifier, or you can say this emitter follower, yes, or voltage follower. Okay, so this is what? Voltage follower or emitter follower. If you see here, and also we can say this as emitter follower. This is my emitter follower or common collector amplifier, or this is what? Voltage buffer. What circuit is voltage buffer? So let's say I'm just representing this like here. This is my voltage buffer circuit, as this is my common collector amplifier as voltage buffer. Okay, common collector amplifier as voltage buffer circuit. Okay, VB here means voltage buffer. VB here means voltage buffer circuit. Voltage buffer circuit. Okay, so now here if you see the input resistance of voltage buffer is how much? That we got how much? 100 kilo ohm, in the order of 100 kilo ohm. And output resistance, how much? Output resistance in the order of 10 ohm. And this is my load. Here is my load. Okay, so this is my load, and this is just as a, this is my what? Loudspeaker. This is output. Load is of 1 kilo ohm load. Now see here, now I am going to connect this input voice signal through what? Through voltage buffer. Okay, common collector amplifier as voltage buffer. Now see, I am going to again rub this voltage buffer. Now we have understood this, like what is the input resistance here. I am just connecting this, and here if you see here this is my this is like this. I'm just representing this by symbol of voltage buffer circuit, and whose output resistance is what, this 10 ohm, and this is my load RL of 1 kilo ohm. Yes, and this is my output. Now see, this is what voltage buffer circuit, okay, whose input resistance is this, and voltage gain of this buffer circuit is how much? 1. Yes, this is my voltage gain, approximately unity. Now see here what we get here. Now at the input side, let's say this is my Vs voltage at input side. How much is this Vs? Vs is equal to, by applying voltage division rule, which is equal to 100 into Vi divided by 200. Yes, 100 means it is 200. Actually this voltage is what? 200 millivolt. Yes, millivolt. 200 millivolt. Yes, this is 100. Voltage division rule, 100 into Vi divided by 200, which is nothing but, if you see here, 100 by 2 means it is Vi by 2. Vi by 2 means we are getting Vs is equal to what? Vs is equal to 200 divided by 2. So which is equal to 100 millivolt. This is what Vs is equal to 100 millivolt. That we got here 100 millivolt of voltage. Voltage at the input of this voltage buffer. Okay, so voltage buffer. So now see here, we got how much? 100 millivolt. Okay, across the input resistance of a voltage buffer. Now see, the gain of voltage buffer is what? Gain of voltage buffer is approximately equal to what? 1, which means what? Here, let's say the voltage is here V01. So this is my voltage V01 divided by Vs. Divided by Vs is equal to what? 1. This means that V01 is also equal to Vs, which is equal to 100 millivolt. Yes, 100 millivolt voltage that we are getting at the output of voltage buffer circuit. Okay, so now see here, at the output we got how much voltage? V01 is equal to 100 millivolt. Okay, so this is what the voltage that we obtained at the output of voltage buffer. So okay, so output of voltage buffer. Now similarly here, by applying the voltage division rule across the load resistance of 1 kilo ohm, that we get how much here by applying voltage division rule across the load resistance of 1 kilo ohm. How much we will get here? V0 is equal to, this is what, 1k into V01 divided by 1k plus here 1k plus 10. Yes, 10 volt. So if you see, this V0 is equal to how much? 1k by, if you see 1k plus 10 is approximately what? 1k only. So this is what V0 is, 1 is how much? 100 divided by, if you see this one, 1k, this is let's say into 1 divided by, this is 1001. Yes, 1k, this is 1000. So if we, this is in millivolt. How much is this? If we say this will come like how much? 50. This is approximately what? This is approximately equal to 99. Yes, this is what? 99 millivolt. 99 millivolt will come. Okay, so if we see this one, so if we divide this, it will come approximately 99.9 volt, 9 millivolt. Okay, so output voltage here, how much we got here? 99 millivolt across this signal. How much we have applied here? 200 millivolt, and at the output we are getting how much? 99 millivolt of signal. Okay, so this V0. Okay, so how much we are getting here? V0 is equal to 99 millivolt at the output. Okay, so which is what, if you see, as compared to the signal that we have applied directly to the load, that time we are getting 2 millivolt, but 2 millivolt by applying 200 millivolt of signal at the input without connecting what? Voltage buffer. But with the help of voltage buffer, how much we are getting? 99 millivolt. Yes, 99 millivolt. This means that how much percentage of this is? This is approximately 50% of. This is what? Approximately 50% of input signal. Yes, means what we get the significant amount of performance. Okay, so in the input signal as compared to the signal that we have applied applied what without voltage buffer. Okay, if we are not connecting voltage buffer here, then how much voltage we are getting, how much signal we are getting here at the output? 2 millivolt. 2 millivolt means how much percentage of signal attenuation is there without connecting voltage buffer? There is a 99% of attenuation in the input signal. Okay, so in the input signal, if we are not connecting the voltage buffer, but with the help of voltage buffer, how much we are getting? 99 millivolt. How much percentage of 99 millivolt with 200 of 200 is approximately 50%. Means 50% improvement that we have obtained with the help of this voltage buffer. So this is what the beautiful application of common collector amplifier. So why the common collector amplifier is important? This is because it buffer the input signal with significant amount of performance at the output side. Yes, so this is the important application of common collector amplifier. It help us to buffer the input voltage with significant improvement that we have seen, significant improvement as compared to without connecting voltage buffer. Okay, so this is what we can say the important application of common collector amplifier. Yes, you see here 99 millivolt of signal that we are getting after applying this 200 millivolt, means we are able to hearing the voice signal at the output across the load. Yes, which is the significant improvement in the signal. Okay, so with the help of this voltage follower, which is because of common collector amplifier, whose input resistance is very large, output resistance is very low, and voltage gain is approximately equal to what? Unity 1. Okay, so now the question may come in your mind, like, is it possible to buffer this signal? Is it possible to get the 100% of signal across the load? Can I just get this signal without any attenuation across the load? Is there any amplifier like that? Yes, I can say yes. There is a amplifier through which we can get the 100% what? 100% strength of this input signal across the loop of loudspeaker. So how it is possible for that? We will see we will see the unity gain buffer amplifier. Yes, unity gain buffer amplifier that you might have seen. Unity gain buffer amplifier. This is my unity gain buffer amplifier. This is positive, this is negative here, and this is my unity gain buffer amplifier. This, and this is what? Load. Yes, load resistance of what? 1 kilo ohm. Load resistance of 1 kilo ohm, and this is my V0. Yes, and here the input signal is connected, whose input resistance is of how much? 100 kilo ohm. So this is my Vi, and this is my Rsig of how much? 100 kilo ohm. 100 kilo ohm. Okay, so this is what? Input signal. Yes, input signal. Here you see this is what? Operational amplifier. I am assuming this operational amplifier as ideal operational amplifier whose voltage gain is approximately infinity. See, whose voltage gain is approximately infinity, whose input resistance is also approximately infinite, and whose output resistance is approximately equal to 0 ohm. 0 ohm. Yes, so this is what the ideal operational amplifier characteristic. Now see, when the operational amplifier is idle and is in negative feedback, then that time the virtual ground concept is valid. What is virtual ground concept? Means whatever the voltage is here, like here input voltage Vi is there, same amount of voltage will appear here. Okay, same amount of voltage will appear here, Vi. So this is the virtual ground concept. If you see the entering current inside the ideal operational amplifier is in the order of microampere or nanoampere, which is almost negligible. So therefore the voltage drop across this 100 kilo ohm resistance is also negligible. So therefore same amount of voltage will appear at the non-inverting terminal of op amp. So therefore due to what? Virtual ground concept, same amount of voltage will appear at the negative terminal of an ideal operational amplifier. So therefore if you see there, this is short and this signal will appear directly here. If you see here 100%, you see 100% of input signal strength is appearing across the load. So this means what? V0 is equal to what? Vi. V0 is equal to what? Vi. You see, so this is the way how we can achieve the 100% input signal strength across the load without any attenuation of the signal, means 0% attenuation in the input signal. That, okay, so with the help of what we are getting this, with the help of a unity gain buffer amplifier. Okay, so where we are assuming that this operational amplifier is what? Ideal operational